Good morning, everybody. Nice to see you here. My name is Leonardo Giannini. I am a PhD student from NTNU Norway, and I would like to take a moment to acknowledge my supervisors, Dr. Antonio Alvaro from Synthetic Industry that you may probably know, and Professor Nicola Paltrinieri from NTNU Norway. So today we are going to discuss a topic that is not really the usual here at the Hydrogen Symposium, because I'm not an expert in material integrity. What I do my PhD in is process safety, and especially with risk-based inspection planning. So today we are going to discuss some of the commonalities, the common points that we have between what you study, what you do research on, and what can be used for the safety of hydrogen technologies, especially for a promising technologies that is hydrogen pipelines. And so we will discuss the topic of risk-based inspection planning that is rooted in concepts of material integrity. And the pipe exploded due to hydrogen, probably. So, well, as it was discussed in the previous presentation, there is an expected increase in the hydrogen demand in the following years, following for big projects such as the REPowerEU plan, a hydrogen strategy for a climate neutral Europe. And this increase in the hydrogen demand will lead to repurposing of the pipeline grid. And so our main scope is just to promote the safety for these technologies. But we have a problem. We have a lack of operational experience concerning hydrogen pipelines and the inexistence of dedicated inspection and maintenance standards. These lacks can lead to uncertainties concerning failure probability and failure consequences. And so to discuss this in a more proactive manner, I have to just tell you what RBI is, what risk-based inspection planning is. So when you have a component that is exposed to a degrading, a harsh, a corrosive environment, such as a hydrogen gaseous environment, you could theoretically use a risk variable to be associated to this component. And of course, this risk value will increase over time. And at the end of a period, this risk value will increase until it reaches an established threshold. And this is the time of inspection. This is the time when you go there, you take a look at what happens, you see the component is still good to go, or we need to do maintenance activities. The problem is that we don't have a methodology to evaluate how this risk evolves with time when it comes to hydrogen systems. We could disregard the hydrogen damages, but this can maybe lead to an underestimation of the risk level, which is maybe unacceptable, or we could be too much conservative. And this can, well, reduce the risk of an unwanted event, but on the other hand, it can raise the costs associated with a safety budget. So just to make this more concrete, I have to tell you how this risk variable is calculated. Well, risk is simply the combination between failure probability and consequence of failure. The consequences of a failure are estimated based on financial consequences, potential for loss of life, business interruptions, and so on. While this probability of failure is based on this damage factor. Simply, this damage factor is what connects the material degradation, the material integrity, with the variables that are relevant for risk analysis. And this damage factor, as you will see in a moment, the bottom equation of the slide is, well, depending on the age of the component, age of the equipment, so the time of exposure to the harsh environment, and to another parameters that is called base damage factor, DFB, which is none other than this number here, which was appearing in the other equation. And so if you look at the existing standards, the most established is the API recommended practice 581. They give you methodologies to calculate this number here. And so you have this evolving factor that then is used to calculate your failure probability. The problem is that they ask you for the pH of water and the H2S contact of water. And this is just an example, but all the hydrogen damages in the methodologies are rooted in these parameters that, of course, are not relevant at all for a gaseous hydrogen transportation. And how can we solve this problem? Well, what I would like to tell you today is that we think that a methodology that is based on what you study, on the matters of material integrity that you publish every day, could be built. And we think that this can help the spread of this promising technology in a safe manner, but we have some problematics that we need to discuss. First of all, we did a literature review, and we noticed that usually on a macroscopic scale, the effect of hydrogen is on pipeline steels is described through, for example, the effect on tensile properties. Yesterday, there was a presentation on embrittlement index, relative failure elongation, relative reduction of area, which is used to describe the hydrogen damage. But also some other researchers researched the fracture toughness, such as in the previous presentation. And different test procedures can be used to estimate the effect of hydrogen on the critical stress intensity factor, for example. Other researchers focused on the fatigue cracking, which is often tested at different loading frequencies and tested to investigate the effect, the detrimental effect of the molecule. And each of these parameters is governed by several variables, such as pressure, loadings, additives, defects and welds, the grade of the seal, and so on. So this will lead us to the main point of this presentation. How can we have an overall hydrogen effect? This is a typical problem in safety because aggregating, comparing, weighting data from different sources is always very, very tricky. And we have a spectrum of different possibilities to do data gathering and data aggregation. An optimal choice, of course, depends on many parameters, decision-making practices, risk acceptance criteria, case-specific characteristics, and of course, the method that is used will influence the output in terms of calculated risk. Here is just an example of different models can be used. And just to give you a taste of what an overall model can look like, we selected a logic tree based on fuzzy operators, and we think that it could look like this. So if you look at this tree, the output of the top of the tree is this base damage factor. So what we would like to calculate, what we want to propose as a new methodology. The branches are the different effects on a macroscopic level: fatigue performance, loss of fracture toughness, reduction of tensile properties. And the leaves of the tree, the yellow boxes, try to figure out what is the hierarchy of the variables governing the damage. And in a first attempt, could be evaluated on a qualitative level. Maybe lately can be evaluated quantitatively. So, as I said, in a first attempt, we could tag each of these parameters with a label, for example, negligible, considerable, relevant, depending on the case-specific characteristics. If we have a pipeline that is, for example, subject to fatigue loading, the effect of pressure and the frequency of the load can be more relevant than the effect of the steel grade on the tensile properties, for example. And entering this logic tree, using these operators to compare the various variables, we could end up with a final output for this base damage factor, which can be then translated into a crisp number and used to calculate our failure probability. This, we think, can be a solution with a bright side. That is the fact that is rooted on data that are published, available, and done by you mostly, but we have some limitation. In the case of variables identification, we still have knowledge gap concerning the roles of parameters and variables on crack propagation. We also have the problem of data gathering, because as it is been pinpointed in the literature, we still have some inconsistencies in testing conditions. And this can actually lead to very big issues when it comes to giving a hierarchy to the data that we use to build the model. And also we have the problem of data aggregation, because we don't have a standard method for evaluating data, and this can lead to subjective estimations of the risk level. And so, of course, more experimental data we have, more we will be able to make an accurate evaluation. So to conclude, we today have a lack of operational experience and established standards, and the RBI applicability to hydrogen pipeline is still limited. A specific methodology might be developed, so following increased availability of data. We proposed just a very preliminary attempt that showcases the problem of data aggregation, and we think that bridging the gap between material science and safety procedures might help the spread of a sustainable and promising technologies, that is hydrogen pipelines. So thank you all for your attention. I'm here for every question. Feel free to contact me. And again, thank you very much for all your work.